So, we have learned quite a bit up to this point. We've talked about the definition of transmittance and percent transmittance, and we said in very early on, these machines use percent transmittance to report their values. And this is how much light is coming through at the other end. And we said that there were problems here. The problem is that it's nonlinear. So over time, transmittance was converted over to absorbance values. And this is the number that we still use today. And when we measure anything using a UV vis, we are reporting absorbance. It comes to us and we plug it up when we order a UV vis instrument, and it's automatically defaulted setting to absorbance. And this is the number that we run and that we read and that we report. And we said that absorbance is really a look at how the molecule is absorbing the light and keeping it and not letting it go. So we made this analogy between the food, right? So absorbance is the food on the plate that the molecule has decided to keep for itself. And transmittance is basically all the food that's left over on the bar that anybody else can use. And these are the two different types of measurements that we can do using a UV vis instrument. Okay, so we said that there was a working range, and the working range for absorbance was around a 0.1 to a 1.5 ABS value. And we said anything lower or anything higher here doesn't quite work. We don't feel good about the measurements and about the samples that we are putting into the instrument. So if it's lower than 0.1, it could be so low that the machine has a really hard time picking up the differences. And if it's higher than 1.5, the same thing can happen. It could be so high that the machine has a really hard time picking up the differences. Okay, so the next problem that we face in a laboratory using UV vis spectroscopy is this concept of absorbance. Okay, so when I make a sample and I bring it in for analysis on a UV vis instrument, this sample better be in that particular working range. If it's not, I need to do something to it. I need to make it weaker and then rerun it. Or if it's too weak, I need to go back to the drawing board and figure out how to make it stronger so that way I can run it and feel good about the data. At the same time, my standards have to be made as well. And the standards also have to meet that criteria of 0.1 to 1.5 absorbance. Okay, so for instance, let's take caffeine. And let's say that I'm getting a can of soda and I want to measure the caffeine content in the soda can. Well, that's my sample. That's what I want to analyze, right? Well, that probably means that in a laboratory, I'm going to have standards of caffeine. So caffeine that I have ordered. And this is a powder that I will use and weigh out and make samples with. And this ordered caffeine are my standards. These standards that I make have to be in that working range. They have to be between 0.1 to 1.5. Everything should be. Well, the problem is that if I really don't know what I'm doing, and I bring in caffeine standard to the laboratory and I weigh it out on a balance, how much is too much and how little is too little? That's the question. So I could go in and just rough guess it and just throw on some caffeine powder onto a balance and wash it out into a volumetric piece of glassware and dilute it to the line and go run it and see what happens. And then if it was higher than 1.5, I would bring it back into the lab, I would dilute it down, and then I would go run it again. And if it's still higher than 1.5, I'd bring it back to the lab, I'll dilute it down, I'll go run it again. And I can keep doing that over and over and over all day long. And that's a lot of trouble. I don't want to do that. I want to make solutions one time and have it ready to go, right? Okay, so how do we know how to make standards, especially, that are within this working range of 0.1 to 1.5? Well, there is a magic equation, and that equation is A equals EBC. Almost like the alphabet. It's a little bit different, though. A equals EBC. We have a special name that we give this equation because it's so important. So important. And the special name that we give this equation is called Beer's Law. Beer's Law tells me how strong and how weak these solutions need to be in order to get something that will run between 0.1 to 1.5 absorbance. That's its purpose. Okay, so let's take a look at these variables and let's talk about what they mean. The A is going to stand for absorbance. That wasn't hard. Probably saw that one coming. So if I want a solution that runs 1 absorbance, I put a 1 into that equation. If I want a solution that runs a 0.5 absorbance, I put a 0.5 into that equation for A. If I want to make a solution that runs a 0.25 absorbance, guess what? I put a 0.25 in for A. So that's my absorbance number. The E. This stands for molar absorptivity. The E, however, also, in some people's eyes, stands for extinction coefficient. These two terms are used interchangeably. Molar absorptivity is the new school way of talking about the variable, and extinction coefficient is the old school way of talking about the variable. So you can automatically probably pinpoint the age of somebody when they begin talking about the E variable. We tend to use molar absorptivity all the time because that's kind of where we want you to be. That's the new trend. That's the new term that's given. And we're trying to stay away from the older terms whenever possible. But they're both out there. You get two different types of people. They both use that term, and you might see both of them. So this extinction coefficient, or the molar absorptivity, is a number, and we'll talk about that number, if not in this video, in the upcoming one, and tell you what it means. We get another variable called B. B is what we call the path length. Again, we'll talk about that eventually in another video. And C, well, C is concentration. And the concentration is a specific unit here, and that is molarity. And we use a capital M for that variable. So if you're unfamiliar with molarity, you might want to take a look at that equation. Molarity is equal to moles of a substance divided by the liter when I make a solution. Moles is another way to report grams in a roundabout way. So I take grams of my substance, divide it by the formula weight of that substance. That gives me moles. And then the liter, of volume that I'm dissolving it in. Okay, that's molarity, and that concentration is reported in molarity for the equation. That is what we call Beer's law. And Beer's law is going to be very important because what will happen is that if I know the absorbance that I want to make, let's say a 1, and if I know the molar absorptivity and the path length of what I'm using on the instrument, then I've got 3 parts of the equation that I could use to solve for the concentration. And this will tell me how strong to make my solution in molarity. Well, if I know how strong to make my solution in molarity, I can backtrack and figure out how many grams of solution or powder that I need to weigh out in order to make this thing work. All right? So we'll do some examples and we'll walk you through how to make those standards. But that is Beer's law. And in the upcoming video, we're going to talk about the purpose of molar absorptivity. What really is it? What is that number telling me and how can I find it? And then we'll also talk about the path length. What is the path length? What is it referring to? You know, what number should I be using in each one of these cases? So that's what we're going to talk about in the upcoming videos. You know, go take a bathroom break. You've listened to me enough maybe already. Go get you a drink of water. Go get you a snack. Make sure it's carbohydrate based because that's what makes your brain work. It might not make your belly flat, but it sure does do wonders for your brain. And then come back and let's take a look at some of the upcoming videos on Beer's law.